Okay, so today we'll be talking about dynamics, the third unit, and in this case, it's more on the topic about force. So, first of all, what is a force? A force is either a push or a pull action. So, for example, let's say you have a box, like for example this thing. Then, when you actually apply some form of force, you are pushing it forward. On the other one, the other action is where let's say you have the box, right, and you are moving in the opposite direction. You want to pull it again towards you, right? That's a pulling action. And then the SI unit for a force is actually Newton. Newton, and the SI unit at the end is actually a capital letter N. If it's a small letter N, right, that will be actually your prefix for nano. So generally, it's actually the SI unit is actually a capital N, and a force is actually a vector quantity. A vector quantity must have two elements to it, two components to it, which is the magnitude and the direction. So direction, how do we share the direction of a force? Is either you indicate as north, south, east, west. Let's say you have a compass, north, south, east, and then west. Okay, in this case, or it can be a symbol, a plus or minus. But most of the time for force, if it's a two-way direction, right? If it's on a plane and it's a two-way direction, then forward will be a plus and backwards will be a minus. Of course, if we do a vector diagram, which we later will see, we usually indicate the direction separately, which is like a north-east, north-south, or usually a compass direction. Now, for a force, it can actually lead to an effect. So that's why we call it to an effect of the force. So there's a few ways in which the effect of a force could actually be done. Okay? For example, number one, it can make an object speed up or accelerate. So imagine yourself pushing behind a car. And when you have so much force, you actually keep pushing, pushing, pushing. This will actually cause the object to initially do, first of all, stationary and start to move. So you have that here. Then later on, as you continue to keep pushing, it will actually help the object to accelerate. Now, in the event that you don't actually push the car back forward, instead you actually push it against its own direction, right? You're trying to generate some form of friction, right? You will then be able to slow down the object. And after, if you have sufficient force, you can even cause the moving object to stop moving at all. Okay. Now, in the event that you're not either the forward or the back of the car, okay, you're at the side. That will allow you to then change the direction of how the object is moved or change the direction of where the car is. The object can be even like, now there's a World Cup fever, right? You can even like change the ball. So you kick the ball, it's like you're applying a force onto the ball. So these are some of the things. Then if your force is great enough, let's say two cars they hit onto an accident, no? They hit at the side, you will see that the whole side of the car maybe get bent inwards or things like this will actually cause the change of the shape of the object. So generally these are the effects of how a force can be applied onto an object. So when we talk about force, there is two types of forces, contact force and non-contact force. So contact force must have two surfaces touching together. And that will actually lead to, in which when you say touching, they are physically touching each other to exert either a push or a pull. And that is actually a type of force, or what we call contact force. So you can see, in order to, when we talk about defining contact force, we must first define what is contact. So that is physical touching or physical contact with one another, and then back to the force, a push or a pull. Okay. Then when we talk about non-contact force, the only word that you have to change is that it's not in constant or not in physical contact, but are able to exert either a push or a pull action. So what are some of these examples? When you say contact, the most common one that we usually see is frictional force, where friction is this opposing force. Okay, and then you have tensional force. Normal force is basically just how you are applying the force only. Then you have the applied force and air resistance. So air resistance in a way is a contact force because it's the air particles that are physically in contact with the surface of the object. Okay. Now, what are then non-contact force? Non-contact force, that means there is no like particle in a way touching it. So you have your gravitational force, which is force generated by gravity, electrical force, and of course your magnetic force like attraction and repulsion. So in any form of forces, right, we always try to follow a few laws. In this case, we have a few laws that you have to remember in exam. Okay, in which Newton's first law. So what is Newton's first law? Newton's first law is called the law of inertia. Okay, inertia is it basically states that any object will remain at rest or uniform motion unless an unbalanced force acts on it. Okay, what this actually meant is that something has to be introduced to cause a change to the overall uniform motion. Otherwise, that object will just keep moving forward. And so that is what they meant by Newton's first law. So let's say if we look at a balanced force, if two individual forces acting on an object are of equal magnitude and in opposite direction, these forces are said to be balanced. So put it this way: you have a box, okay, and you are doing a tug of war. So one person is pulling towards the left, the other person is pulling towards the right. But as a bystander, you see that this box is actually not moving. It actually stays stationary at its position. Then the question is there a force being applied? The answer is yes. There's a force being applied because there's person A that is pulling towards himself and person B that is also pulling towards himself. It's just that the amount of force, which is F1, is equals to F2. So this is one way in which we showed that because F1 is equals to F2, this scenario the forces are actually balanced. It can be also a simple thing whereby right you have a book resting on the table, okay, in which right the the weight of the book is a force, correct, and the table the counter force that's applied by the table is actually moving upwards. So this will actually cause it such that because it's balanced, the book is resting on the surface of the table. In the event that the weight of the book is greater than the force of the table, the book will break the table. If the force of the table is greater than the book, then you will see the book actually floating upwards above the table. So in in all, when you always see the book resting on the table, it's because these two forces are balanced. But then it can also slide around on the surface of the table, but it doesn't. Why? Because there is two forces acting on the sideways of the book, resulting in it being stationary. And in this case, it is frictional force. So the frictional force is actually balanced in both the front and the back of the book. Okay. So your Fn is your normal force and your W is your weight, in which this one, when these two forces are balanced, you don't see the book moving up or down. Then of course, if you look at the side one, which is the Fa and Ff, you would see that they cancel each other as they are of equal magnitude, acting in opposite direction. Therefore, they are balanced, and hence the book is resting on the table. So always remember the four dimensions. Okay, the four way to explain a form of stationary if you are required to explain. The side one not so much. So it's usually in exam scenario they usually do in either two plane only lah. In which if it's from the bottom right, they will either talk about weight and air resistance. If it's the left and right one, it's either frictional force versus an applied force. So these are the kind of situation. And if an object is moving on a horizontal surface, we would see that Fa and Fr, they actually balance each other as they are of equal magnitude but act in opposite direction. And that is why they are constant. Sometimes this can also mean that the object is moving constantly. There's no added acceleration. So the force acting on the object are balanced, and it can still continue to move with a constant speed where the acceleration is zero. So it doesn't mean that if Fa equals to Ff, right, if they are the same, right, means that the object is stationary. No, it can still be moving It's just that it's not gaining any form of acceleration, and assuming that the horizontal surface is frictionless. Okay? So that in this case, you don't see the object changing shape. In any case, for an unbalanced force, an object will be said to be experiencing an unbalanced force when one of the force acting on it is not balanced by the other of equal magnitude. Okay, and it has to be in the opposite direction. So this will then cause the object to accelerate or to move faster in some place. For example, if the weight is greater than the air resistance, the object will actually be accelerating downwards or falling from a height. Okay, and how to go about explaining this kind of scenario? Number one, you have to state the first one is comparing the magnitude of the force. So that's the first one. The second one is you explaining whether the force are equal or cancelling each other, or not cancelling each other. That means they are, if they are not equal, then the third part you say that is it balanced or not balanced in terms of the force. And lastly, you talk about the acceleration plus the direction. So this is how you phrase your answer. Compare the force in terms of the magnitude. Second, is there any cancellation or is it the same? Third, is it balanced or not balanced? And lastly, what are some of its effects? Is it stationary? Is it moving at a constant velocity? Or is it accelerating in what direction? Same scenario over here. So that's Newton's first law. Then now we look at Newton's second law, where forces have both magnitude and direction. And in this case, this we already established it's actually a vector quantity. And two or more force acting on the object can be combined into a single force, which we call resultant force. So resultant comes from the word result. So something. So when you look at result, it must be something plus something or something minus something, where we actually find the overall net force and in that direction. So in this case, when we see F1 moving in the same direction, we would see that the overall direction of the force will be moving to the right. Whereas if we look at F1 and F2 squeezing towards each other, it's very hard to determine in this case unless we can actually tell whether F1 is greater than F2 or vice versa. And that will result in a change in the shape of the object. Okay, so if we so generally when we are trying to do this kind of forces calculation, if they are in the same direction, we add them up. However, if they are in the opposite direction, we minus them. So when the resultant force acts on it, the object will accelerate in the same direction of the resultant force. So that's what we call the overall. So let's say 8 Newton is moving to the right and 5 Newton is moving to the left. We would see that the overall difference between them is 8 minus 5, which is 3 Newton, moving in a direction towards the right. Why? Because F1 is greater than F2. 8 is F1, 5 is F2. And in this case, when we look at Newton's second law, right, it states that the acceleration of an object is directly proportional to the resultant force acting on it and inversely proportional to its mass. In a nutshell, what this means is it's represented by this equation that you have to remember, which is force equals mass times acceleration, where the SI unit for force in this case is in Newton, mass is in kg, and acceleration is in meter per second squared. So force is equals to mass times acceleration. One common thing that students usually get it wrong here is either you use the wrong units. Weight is not mass. Weight actually, right, is in another formula. It's called weight. From this same application equals to mass times gravitational strength. And what we see is that gravitational strength of Earth is actually times 10. That's why and it's actually the gravitational acceleration. So it's then mass is mass of the object, and of course weight is the overall force. SI unit, same thing. SI unit of weight, because it's a force, is in Newton. Mass is mass, so kg. Gravity will be the same again. Okay. So let's look at this question. How is it done then? First of all, you'll see that a car of mass 2 times 10 to the power of 3 kg, which is about 2000 kg, and the resultant force created by the engine is 3000 Newton. So you have two indicators here already. One which is the M, and the other is the F. Calculate the acceleration caused by this. So if you apply, so you can write something like since Newton's second law, F equals ma, and given that F is 3000 Newton, M is 2000 kg, acceleration will be force divided by mass, and you'll get this 1.5 meter per second squared. A man applied a force of 50 Newton to move a carton of mass 10 kg at a constant speed. So if you see constant, right, speed especially, or constant velocity, the first thing in your mind you must register is that acceleration is equal to 0. Okay, what's the frictional force caused by it? So first of all, since the box moves with a constant speed, acceleration is 0. And because acceleration is 0, given Newton's second law, F equals ma, acceleration would become 0, therefore the overall force will also be 0. So since resultant force F equals to the force applied, that means the overall force that you actually exert, that the man actually applied, minus away the frictional force caused by the carton of mass, it will just be 0 equals to 50 minus frictional force. Therefore, frictional force is 50 Newton. Because in this case, we would see that they balance out in a way. Okay, you can pause the video to try out some of these questions as well, and this as well. So in summary, when we look at it, the balance force, right, the object will have 0 acceleration. In this case, there's two things that can happen to the object. Either it is stationary, not moving at all, or the object is moving with constant speed. That means acceleration is also 0. So this is what happens during a balanced force. For an unbalanced force, the acceleration is really determined by two things. By number one, the mass of the object, or the resultant force on the object. So generally, this will actually show that it can be influenced by quite a few things. Okay, then of course, you can try out some of these questions. Then we will be moving on to our next session, which is Newton's third law. So Newton's third law states that forces are always produced in pairs with opposite direction and equal magnitude for action and reflection force. That means, right, for every force moving forward, there is another opposing force. So this is the main idea of the law, third law, in which forces must always occur in pairs, equal and opposite, or act on different objects. So how to establish this then? You can actually use free body diagrams to help understand or to show the relative magnitude and the direction of all the force acting upon an object in the given situation. For example, when we look at this, the direction of the arrow gives the direction in which the force is applied. When it's moving upwards, it can be a sign of lifting, okay, or air resistance if it's moving against the object. W here would be the weight, which is represented by W equals mg. Then of course these two, one, it can be Fa will be the force that you apply to push it, and of course Ff, which is the frictional force. So you can see the kind of pairs that you have is like the lift will be with the weight, the force applied will be against with the frictional force. And all these, when if we look at the previous law, first law or second law, we'll see whether is it a balanced or unbalanced force, given which of these strength of the force is of a higher magnitude. And next, we take a look at the graphical method in trying to solve some of these items. So forces, because they are generally vectors, they can be applied to determine the resultant force. And in this case, first of all, you must always establish the scale. The scale, it can be either given in an exam, but it's usually represented by a ruler. For example, for every 1 cm of ruler, how much force do you want to determine? In exam, most of the time is they will have already given you a existing line. So what you have to do is you take a ruler, you measure the existing line, the amount of force, then you divide accordingly according to the measurement unit. So let's say you measure 5 and it's used to represent 3000 Newton. So to convert the scale, it will be you want to find 1 cm is how much. So let's say you measure 3000, you measure 5 cm for 3000 Newton representation. This is given in the question. This one is through the diagram which you use a ruler to measure. Next, you have to calculate. So what you do is for 1 cm, it's just basically 3000 divided by 5, that will be 600 Newton. So that will be the scale that you have to use consistently. But that doesn't mean that you have to that is the final answer. Rather, in exam, there is two ways to determine the overall direction, which is the parallelogram method or the tip to tail method. So let's look at parallelogram. So in exam, they usually give you two directions, an A and a B. They will tell you what is the overall angle here. And if don't have, right, it is usually given in the, it's required of you to draw in the exam. Okay, usually you use a protractor, you use your set square to mark the difference in the, what do you call it, the length, and then you can where to go. So what is this parallelogram method? So this parallelogram method is where in the existing line that you draw, you take a set square and you measure another length that is parallel to this, of the same length in the same direction. And this is the one for B. Then you repeat the same one for the one for A. So again, you use your set square and then you just triangulate, you draw it to the right. But do take note that this has to be dotted lines, because these are all working lines and it's not actual force line. So do take note of that. It should be dotted line. Then later on, there will be a point in which they will have intersect, which is over here. So what will happen is, based on the original point, you draw an overall resultant length and then you mark it with a double arrow. A double arrow will indicate to readers that this is actually a resultant force, and at the same time it has to be a solid line. So with the scale that you have, you take a ruler, you measure this resultant force. So if let's say this is 7 cm, then you have to take, since 1 cm is 600 newtons, so 7 cm will be 7 times 600, it will be about 4,200 newton in terms of force. Then your final answer, you cannot just say 4,200, you have to state the direction. That's with referencing of one of the point. Okay, then that would be for parallelogram. For tip to tail, on the other hand, it's more of another method where it comes from the name tip. So you choose an appropriate scale to represent the force A and B, like what you say, but you place the tail of force B onto the tip of A. That means the tail of force B, which is this one, you put it up to the tip. Tip means at the starting arrowhead of A. So you bring the whole of B upwards. And then what you do is you join the start point of A to the end of B to obtain the resultant force. Okay? And that's what you get. And then you convert the length to units of force using the scale. So the method is about the same. So generally, it's same way, more or less the same way of actually getting for the step 1, 2, and step 1, 4, and 5 with the other steps. It's only the way to actually draw the diagram will be different. And in exam, usually they will measure differently. So when you do your 10-year series, you will see that sometimes your answers are a bit off. It's because in O level, the size of the diagram is drawn to scale. Okay, so that is one thing you have to take note of. Okay, and finally, we will be talking about friction. So, friction, on the other hand, it is a force exerted by a surface or fluid medium such as air as the object moves across or through it. So, friction is an example of a contact force. And friction is caused by rubbing between the surface of metals. Okay, and another way of friction is that for frictional force, they tend to be opposing the motion of the object. Sometimes air resistance or drag is actually the force caused by fluids such as either the air particles or the liquid. Okay, so it doesn't mean that only solid surface will actually exert any friction. So the two types of friction are static friction, which cause the object at rest when a force is applied, or dynamic friction that can actually cause the object to move at a constant speed when a force is applied. It also causes energy to dispel as to dissipate heat to the surrounding because it is actually touching each other. And when the speed of the object increase, friction would also increase. So you will actually generate more heat. As some for a nuisance is that it will actually cause a lot of wear and tear. Okay. So when friction is useful, it's like for example you enabling you to walk without slipping, or even to pick up things such as objects using chopstick or what's not, or even your mug. When friction is a nuisance, that means something that is negative. It's like it will actually cause a lot of wear, and this will need you to actually replace your equipment, your objects, and at the same time, it can also convert all your useful energy to waste energy in the form of heat. So you are losing heat energy. So some ways to overcome this nuisance, we can actually add ball bearings or wheels to try to actually reduce the friction between the surface. The other one is air cushion, where air is actually a very bad, it's in a way a layer to reduce friction, and of course lubricating oil and grease. So again, friction can be calculated based on the F equals ma formula again. There are a lot of questions that you can actually try in your 10-year series work. And I think that those will be quite relevant and useful. Okay, so that comes to the end of this particular chapter. You can read through and do read your Martian Cavendish textbook for more of the information and details. Thank you.